Right. Now onwards, let's discuss what is the next topic is our session. What is the next topic is partial autocorrelation function. So we have discussed autocorrelation function. Then let's discuss what is partial autocorrelation function. Actually, partial autocorrelation function is, you can see it as a partial autocorrelation function is the autocorrelation between two data points, condition of in between data points. You can see, if you suppose yt and yt plus n, then there are some data points in between yt and yt minus, sorry, t plus 1. Then we have to consider these two points as well, right? For example, suppose like this. So we have, sorry, this, right? Okay. Then I'll draw it like this. We can consider like this. Right. Suppose this is y at t, and this is y at t plus a. Then what is this point? This is definitely t plus 1, t plus 2, and so forth. Then in here it should be y t plus n minus 1. Right. Then what PACF says, once a partial autocorrelation is saying that it's also autocorrelation, right? It's also autocorrelation. It is also autocorrelation. You know what is this autocorrelation? Auto in the sense we are considering the same time series. We are considering the same time series, right? We are considering the same time series. Then correlation in the sense the relationship between or dependence between these some random two values. Then in here what we are considering, yt and yt plus n, these two. Then in calculating PACF, actually I am discussing this point, you should have somewhat of understanding what happened inside this function, right? Then we discuss what is ACF plot, autocorrelation plot, right? In the autocorrelation, what happened? We are considering previous error component. Based on that, we are identifying what is the order Q, in the sense how many previous error components should be considered to predict the next value based on the moving average process, then with the order Q, right? Right now we are discussing about AR process, and we are going to identify the parameter P, right? This is the parameter of AR process. And how do we identify it? Then the way of identifying P value or value of the P parameter is using PACF graph. PACF, partial autocorrelation function. Then you should have somewhat of understanding what is this. So that's what I am going to discuss in here, that partial autocorrelation. What they are doing is they are calculating the autocorrelation. They are calculating the autocorrelation, right? Autocorrelation But this is not the simple autocorrelation, but they have condition on in between these values. It is somewhat of a conditional autocorrelation. It's somewhat of a conditional autocorrelation. Then what AR process says? In AR process, just recall previous lecture. In AR process, what we discussed, we are identifying some set of previous data points in order to predict the next value of that time series. Then this previous data points, number of previous data point is representing by the p-value. P-value in the sense not that statistical p-value, that parameter p. Then if p is 1 in the sense, we just considering previous 1 value. Then if it is p equal to 2, then we just considering previous 2 values and likewise. Then in the PACF function, they says us what is the optimum number of previous values to be considered in the AR process. Then how he calculate this autocorrelation using this PACF function like this. It depends and based on or condition on in between these values, he is calculating this correlation of YT and YT plus A. That's what happened in the PACF function. Right. Then let's try with some simulation to check whether exactly it happened or not. Right. So in order to simulate, prior to that, actually, let's see what is the equation where we have to use for that. What is the equation for AR1? Oh, yeah, AR1 process. What is the equation for AR1 process? AR1 process. What is the equation? Then we are going to predict YT. It should equal exactly the previous data point plus error term. Then alpha 1 y t minus 1 plus epsilon t. Then this is noise component. This is the previous value, previous data point. This is the previous data point. This is the parameter. This is the coefficient. This is, now we are going to simulate this equation with Python code. Right. Then what we are going to do is simulating or simulate AR1 process with PACF. All right. Then what is the equation for that? Equation is y underscore t, no need to capital Y, y underscore t. Then alpha 1 times y t minus 1 plus epsilon t. This is the equation that we are going to simulate, right? Then what actually does it say? It says actually the process linearly depend on the previous values, right? That's what it says, because you can see that process, it depend with the previous values and noise. Okay, right. Then in order to predict this, let me generate some empty cells. All right, good. Then this is AR1 process. So there should be in the AR1 process, there should be one previous value. Then I am setting that initial values underscore AR1 process, right? Then YT underscore one, something like this. This is just variable, right? Then initially there is a zero value, because there should be one previous value, YT minus one. Then for each in, sorry, for I in range, let's go with 1000 data points as usual. Then what we have to do is we want to simulate the equation y equal set alpha to 0.5 as usual. You can play around whatever the values, right? It's totally up to you. Then yt minus 1 instance y underscore t underscore 1, the last value, right? For the right now, the last value is 0. Then epsilon should be a random noise, standard random noise. Then I'm going with the numpy, sorry, rand in some random number, sorry, and I'm adding 0.1 standard deviation as well. Okay, then equation is fine. Then we have to store these values to array y underscore t underscore 1 append y. Then I'm converting it to numpy array. Same one. Right. Then let's just plot it to see what is there actually. So you can see it's also a stationary process, most probably. The mean is 0, I think, I guess. It seems 0, and there is so much variance. Some variance because it's obvious we are using with the random noise, right? Random standard random noise. Right. Then let's try with the PACF graph. That's our ultimate goal is to test. Right now, up to now, what we are knowing is we are simulating what AR1 process, which means we are going to predict the next value based on just previous value. In that scenario, that PACF graph should represent that with the leg 1, right? Then let's try whether it happened or not, right? Then it should be not 10A2, it should be this. It should be this. It should be PACF, right? We have imported it in here previously, right? We have imported, it is available there. Yes, that's That's good. That's pretty good. You can see it comes here. As usual, I said previously as well, there are some outliers, but we can actually neglect or omit them because it's very close to confident level. Compare with this value, this is spike, it's very far away from the confident level. Then it says that this is leg one. Then if you rerun the things again, the output may vary. See, right now it goes there. That's what I say. It's somewhat randomly happened because we use that 95 confident level. Then there is a 5% of randomness there, right? Then it can happen. Then we can actually just omit it. Compare with this spike, it's we can actually omit it, right? Then this is a AR1 process, right? Then just let's try with the AR2 process then in order to verify, right? In order to verify, that's only in order to verify. So I'm not going to write the equation again, but I'll discuss through this, right? Then what would be the equation? We'll just write it in here. What would be the equation with the AR2 plus? I'll take another one. What would be the, let's go like this. AR2 process, what would be the equation? AR2 process, what would be the equation? Then in here it should be yt equal alpha 1 t minus 1 plus alpha 2 t minus 2 plus epsilon. That's all. Very simple. Right? That's all. Then how do we alter this? It should be 2 and in here, is it 1 initial value or 2 initial value? What do you think? This is AR2 process. This is AR2 process. In that scenario, there should be 2 previous value to initiate the process, right? There should be 2 initial values instead of 1. Then I will change this to yeah, as well, right? Then right now we have process with AR1. Then we have to add another previous value. Just let me copy and paste it here. Then I will set it to minus to get somewhat of a deviation, right? 2 and the second previous value. I think that's all. What we have done is we are going to simulate AR2 process so that there should be 2 initial values. That is there. Then we are simulating the 1000 data points. Then this is the equation with respect to this. With respect to this, right? There should be previous, and this is the second previous. Alpha 1 you can set, alpha 2 you can set. This is random noise. Okay. Then I have set the first parameter as 0.5, the second parameter is minus 0.3, and these two initially these two to 0 0. Then I get the random value with the standard deviation of 0.1. Then I append it to that array. Then I convert it to that numpy array. Okay, good. Then let's plot it. Then see what happens. As what we are expecting is actually there should be 2 legs, right? 2 legs. There are, as is, there are outliers as well, but you can see there are 2. There are 2 legs available. Let's read on this. See, it's changing, right? That's what I say. It's randomly happened, but these 2 is constant. It's clearly identify that leg 1 and leg 2, right? Then what would be the p-value? There are 2. then what would be the p value? Because in the real world scenario, what happened? In the real world scenario, what happened? We have the data set, then we perform in PACF and ACF graph to identify P and Q value, right? In that case, we perform in this one is first. Then we are retrieving these two. Then we should have the idea how do we decide which one we use, one or two. The convention is usually, the convention is you can identify P as the maximum non-zero leg. Then what is the maximum leg, non-zero leg in here? It's 2, right? It's 2, 1, 2. This one, non-zero leg. Actually, it should be outside the confident interval. It should be outside the confident interval. This is how you have to select it. It's obvious for Q value as well with the moving average with the ACF graph. You can play around actually with these two values, but most probably it is better to select this maximum non-zero lag value in both scenario, right? So that's all. Actually, I just wanted to let you know that throughout this lecture, actually, finally, what we can conclude actually, with these explanations, with the ACF and PACF graphs, what we can conclude is it's confident enough. These techniques are confident enough to identify or determine the P and Q parameters of AR and MA processors, right? These techniques are confident enough to identify or determine the P and Q parameters of AR and MA processors, because we simulate it. We simulate and we test it. How do we test it? First, we test with the ACF plot with known values. We define first MA1 process, right? In here, with the first, actually what we did is with the random noise, we check whether if there is any lag, whether autocorrelation function identify any lag, but it did not identify any lag, which means that because it's a random noise, there is no any relationship, there should not be any relationship, then it totally identified there is no any relationship. Then actually I altered this. Very first time we had MA1 process, then in there we didn't have this phase. Then what happened, he identified only lag 1, because we simulate lag 1 process, MA1 process, moving average 1 process. Then ACF graph completely identified. Then MA2 process with ACF function, he identified there are 2 lag values. Sorry, 2 lags. At lag 2, he identified this is the process, MA process with order 2. Then the Q parameter is 2. Then it's clear enough that ACF function is clearly identify the correct lag, correct Q value, right? Then we move to PACF plots. Then we discuss what is this PACF plot and what are the conditional of these things and what is the condition and what are the behind the scenes things. like for example that yt and yt plus 1, the correlation between them, autocorrelation, it is a conditional autocorrelation in between values as well. Then we simulate AR1 process with the PACF to identify whether PACF graph clearly identify and reflect whether it's a AR1 process or not. And same thing apply to AR2 process as well. Then it clearly identify it, show in this graph. We can illustrate that PACF and ACF graph is good alternative option to identify P and Q parameters in AR and MA process, so that we can incorporate it with the ARIMA model as well. So that's all I just want to discuss throughout this lecture. So I hope you all get better understanding about ACF and PACF graph with the context of time series modeling under ARIMA model, right? Because we can go differently with in distinct path with the MA and AR, but the combination process, what we discussed last lecture, ARIMA process is much better, right? Then what was the issue there at that time? There was no proper way to identify the P and Q value. Right now we have that. Then in the next lecture, most probably we will discuss auto ARIMA and with the seasonal component most probably. Then in that time you will learn how do we automatically identify this P and Q value rather going with this graphical representation, and how do we implement it automatically, right? Then how do we identify this P and Q value? We will usually go with the maximum non-zero lag, but you can play around with the other non-zero lags as well, but confidently say that only non-zero lags, right? It should be far outside this confident interval, right? That's the summary of this lecture. So thank you very much all. Okay, see you there.